Hey everybody, limits and differential calculus day number 6. Topic for today is kinematics, also known as particle motion. We're going to be dealing today specifically with position, typically referred to as S of t or x of t. That's our position. Our velocity, which is referred to as v of t, which is the derivative of position or change in position. And we'll also be dealing with acceleration, which is equivalent to the derivative of the velocity or the second derivative of the position. Okay, so let's get into it. Pretty short set of notes today, so it should be swift. So kinematics, just formal, is the study of how objects move. A particle moving in a straight line is the simplest type of motion. There are other types of motion, which you'll see in future units. To describe simple linear motion, you need a starting point, a direction, and a distance. So let's define a few things. First, a path. Path is the set of all points along which an object travels. Distance traveled is the length of the path between particle and its starting point. And displacement is the difference between an object's position and its starting point. So, for example, if I walk to school 2 miles, let's sketch it here real quick. I walk 2 miles to school. I forgot something at home, so I walk back another 2 miles, and then I walk back to school 2 miles. Okay, my distance traveled would be 6 miles, but my displacement would be only 2 miles because I'm only 2 miles from where I started. There's where I started, there's where I ended. So my displacement is clearly different than my distance traveled. Okay, let's look at a little bit more here. Position, as we talked about on an earlier slide, typically referred to as S of t or x of t, because there might be a particle moving along the x-axis. That's why they would call it x of t. Velocity is typically referred to as s prime of t or v of t. And acceleration, referred to as the second derivative of the position, the first derivative of velocity, or a of t. Now, just some specifics here with speeding up, slowing down. We're not going to look too much into it. I'm just going to give you the basics of this. But an object speeds up when v of t and a of t have the same sign. So if they're both positive or they're both negative, that's when an object is speeding up. Slowing down when they have opposite signs, either plus and minus or minus and plus. Okay, let's get into a couple of examples. Okay, so let's look at an example. Number 1 here, a particle moves in a horizontal line, so its position from a fixed point after t seconds, where t is greater than or equal to 0, is s meters, where s of t is 5t squared minus t to the 4th. Okay, so just so we know where we're going here, we're starting when t equals 0. And if I plug in a 0, I get 0. So the initial position of this particle is at 0, 0. You can imagine it's traveling along the x-axis if you'd like to. It says find the velocity and the acceleration after 1 second. So s prime of t, which is equal to v of t, is equal to 10t minus 4t cubed. It wants to know what the velocity is after 1 second. So that would be 10 times 1 minus 4 times 1, which would be 6. So we would have 6 meters per second would be the velocity after 1 second. Okay, now we didn't talk about this on the last slide, but if velocity is greater than 0, that means in this case, in this context, the particle would be moving to the right at t equals 1 second. Okay, let's find the acceleration, which would be the second derivative So the acceleration would equal the derivative of 10t minus 4t cubed, which is 10 minus 12t squared. So the velocity, the acceleration 1 second after the particle begins to move would be 10 minus 12, which would be negative 2 meters per second squared. Okay, part B says, hence, is the particle speeding up or slowing down? We would say that the particle is slowing down since V of 1 and A of 1 have opposite signs. Okay, let's look at C. Find the values of t when the particle is at rest. Excuse me. If the particle is at rest, then that means the particle is not moving either direction, which means that velocity should equal 0. All right, so if our velocity is equal to 0, which we've defined as 10t minus 4t cubed, what we can do is do a little factorization. I'm going to take out a 2. That leaves me with, oops, I'm going to take out a 2t, sorry. That leaves me with 5 minus 2t squared. Okay, so clearly the particle is at rest at t equals 0. We're actually not going to use that as an answer. We're going to look here and now solve using the zero product property what the answer would be to the following equation. So where would 5 minus 2t squared equals 0? Well, I could subtract 5 and divide by a negative 2. So 5 halves equals t squared. So at t equals the square root of 5 over 2, the particle would be at rest. I don't care about the fact that I'd get two answers, positive and negative, because time isn't going to be negative in any context that we work with. Okay, so at t equals square root of 5 halves, the particle is at rest. I'm going to abbreviate particle is at rest. Okay, let's look at part D here. Find the time interval during which the particle is speeding up as well as slowing down. So I'm going to do a sine diagram here. And I'm going to look at where velocity is positive, where velocity is negative, where acceleration is positive, and where acceleration is negative. So the first sketch is I'm going to sketch V of t's sine diagram here. I know V of t equals 0 at t equals the square root of 5 halves. Okay, so I could test to the left and to the right. If I took the square root of 5 halves, that would be greater than 1. So let me test t equals 1. Well, I've already done that. And the velocity at t equals 1 is positive. So it will be, the velocity will be positive everywhere from t equals 0 up to, but not including t equals square root of 5 halves. I know it'll be positive in that interval. I'm going to then test the velocity at, let's say, t equals 3. At t equals 3, the velocity would be 30 minus a larger number, so it would be negative. So I know the velocity will be negative after t equals square root of 5 halves. Okay, now let's look at acceleration. In order to determine where there's a sign change in acceleration, I actually have to solve for where the acceleration equals 0. So let's set the acceleration function equal to 0 and solve for t. Okay, so that would be t squared equals the square root of, t squared equals, that would be negative 10 over negative 12, which is the same as 5/6. okay, which is less than 1, so t is equal to the square root of 5/6. That's where acceleration will be 0. So right over here at t equals the square root of 5/6. That's the only place that the acceleration equals 0. Okay, so I'm just going to test one value to the left and one value to the right of the square root of 5/6. Okay, so I'm going to test, actually, let's see, I've already done the acceleration at 1. Okay, so here's t equals 1, and I found that that acceleration was, negative. I just have to test a value between the square root of 5/6 and 0. All right, so I'm going to go with 1/2. If I plug in a 1/2, okay, t equals 1/2 into my function, okay, I would have 10 minus 12 times 1/2 squared. That's going to be the acceleration at the time 1/2 seconds. All right, that'll be 12 times 1/4, so that'll be 10 minus 3, which will be 7. So I see that the acceleration at 1/2 second is positive. So now I have to determine when the particle is speeding up. Well, when the particle is speeding up, we would have the same sign. So the particle will be speeding up in a couple different places. First, from 0 to the square root of 5/6. Okay, I'm going to highlight that here for you. So from 0 to square root of 5/6, we see that the sign is the same. Okay, now from square root of 5/6 to the square root of 5/2, okay, in that interval, we would have the particle slowing down. Slowing down from the square root of 5/6 to the square root of 5/2. Okay, but there is another portion that's speeding up. Okay, we can see that both the acceleration and the velocity are positive after the square root of 5/2. Oops, I don't want highlighter. Let's go back to pen. Good. Square root 5/2 to infinity. Okay, awesome. Let's look at another example. A person jumps from a diving board above a swimming pool. At time t seconds after leaving the board, the person's height above the surface of the pool, modeled by S of t. S of t equals 10 plus 5t minus 5t squared. Okay, so I always do this. I always plug in 0 just to get an initial location, right, or initial position. So S of 0 equals 10. To me, that tells me that the diving board is 10 feet above the surface of the pool. Look at that. I just found the height of the diving board above the surface of the pool, giving me the answer to part A. So 10 feet. Cool. Part B, the time between the person leaving the board and hitting the water. Okay, so we want to know when S of t equals 0. All right, so when does S of t equal 0? Okay, so let's take S of t, which is 10 plus 5t minus 5t squared, set it equal to 0. I'm going to factor out a negative 5 and rearrange so I have my leading term in front. And I get this. Okay, so I'm going to factor this to be t minus 2 and t plus 1. Okay, within the context of this problem, would it make more sense for the diver to be in the air for 2 seconds or for the diver to be in the air for negative 1 second? So let's make a logical decision here, and let's choose that it would take 2 seconds for the board, or for the diver to leave the board and then hit the water. Okay, let's look at part C, the velocity and acceleration of the diver upon impact. Let's interpret that. Okay, so v of t, which is equal to s prime of t, will be equal to the derivative of the function that I see above. Okay, so the 10 will drop off, right? I'll get a 5 minus 10t. That's my acceleration here. Okay, a of t, which is equal to the derivative of v of t, which is equal to the second derivative of s of t, will be equal to negative 10. Okay, so a of t clearly on impact was at 2 seconds, is going to be negative 10, and that'll be negative 10 throughout. Okay, v of t, or v at 2 seconds, will equal 5 minus 10 times 2, which is 20. So v of t will equal negative 15. Now, in the context of this problem, that means that the diver is speeding up, which we would anticipate would be true, right? Gravity's taking over at x, oops, I'm sorry, not x, t equals 2 on impact. Okay, since v of 2 and a of 2 are the same sign. Okay, one more example, and then you'll be able to go on to your homework and get some work done with that. It says a particle moves along a line, so its position s of t at any time t is in seconds is equal to s of t. It says find v of t and a of t in terms of t. That's simply going to be finding those derivatives and not utilizing them yet, but just writing them out. So we get 3t squared for the velocity function, minus 14t plus 11, and the acceleration function, which is s double prime of t, which is acceleration, will be 6t minus 14. Find the time or times when the particle is at rest. Okay, so we're going to take velocity, set it equal to 0. 3t squared minus 14t plus 11, set equal to 0. Let's see if we can factor this. I'm hoping so. How about minus 11 minus 1? I like that. It looks like to me that the particle is at rest at t equals 11/3 seconds and at 1 second. Those are turning points potentially. So the particle could be heading to the left, pause and rest, and then head back to the right, or the other way around. So let's find the times when the particle is speeding up and slowing down. Okay, again, sign diagram analysis here. So v of t is equal to 0 at 1 and 11/3 seconds. Okay, we start at 0 clearly. So let's test a half. Okay, if I plugged in a half, I can do this actually relatively easily. If I plug 1/2 in here, I would get a negative value. If I plug 1/2 in here, I would get a negative value. If you multiply two negative values, you will get a positive for the velocity. So this is v of t. Okay, now let's plug in 2. If I plug in 2, all right, if I plugged a 2 in here, I would get a negative and a positive, which would be a negative. This is just a different way to look at finding sign diagrams for velocity, acceleration, all that good stuff. Okay, what if I plugged in a 11/3 is just short of 4. So if I plugged in a 4, I'd get 2 positives. 2 positives multiplied together would give me a positive. Okay, and since those are the only values where v of t equals 0, I don't have to worry about the rest of the interval to the right of 11/3. Okay, let's look at acceleration. Acceleration is 0 at 0. Acceleration is 0 at the value for t that makes this equation satisfied. So it looks like at t equals 7/3. Okay, so at 7/3, we're going to have a potential point of inflection. Okay, let's test on both sides. If I plug in a, let's say 1, I would get a negative value. So if I plugged in 1 into a of t, I get a negative here. If I plug, let's say 3 in, I would get a positive value. Okay, so now I just need to know where these two have the same sign, where they have different signs. Okay, so clearly I can see from 0 to 1, they have different signs. So we can say that the particle is slowing down. Maybe we can highlight that. We'll see. From 0 to 1. Let's see where else they'd be slowing down. Now 11/3 is greater than 7/3. Okay, so I can actually, I'll go on the bookend here. Let's go speeding up. Well, clearly from 11/3 on, okay, from 11/3 off to infinity, the particle is speeding up. Now I got to work out everything in between. Okay, so they're going to be the same sign, right? Negative from 1 to 7/3. Okay, so I can say from 1 to 7/3, both the acceleration and velocity are positive. And then from 7/3 to 11/3, from 7/3 to 11/3, the acceleration is negative, but the velocity, the acceleration is positive, but the velocity is negative. So I could say from 7/3 then to 11/3. So there you go, slowing down, speeding up. Okay, find the values of t when the particle changes direction. Okay, so this isn't that challenging. And the reason is because the velocity at all of its zeros changes signs. Okay, so the particle is moving to the right for 1 second, moving to the left from 1 to 11/3, and then moving back to the right. So the particle changes direction, okay, changes direction at t equals, 1 and 11/3. Now, the thing you need to be careful for in questions like this is if, for example, the velocity may equal 0 at A and B and C, but if something like this happens where, yes, the velocity is 0, but the particle is moving left, pauses, then continues to move left, that's not a change in direction, so beware of that. Okay, let's look at the last question. Find the total distance traveled in the first 3 seconds. Okay, so in the first 3 seconds, distance traveled is going to be determined by velocity, right? So which direction is it moving and how fast, okay? So what I'm going to want to do is I want to know where the velocity equals 0 in the first 3 seconds. Velocity equals 0. For what t values is the velocity equal to 0 in the first 3 seconds? Okay, so let's just analyze this. Okay, and let's look at the diagram from above. Particle moves to the right for 1 second. Well, we could find that distance because we know that the initial position of the particle, let's figure out what that would be. Let's find the position at the start. Let's find the position after 1 second. And then let's find the position after 3 seconds. Now I know that the particle is moving to the right during this timeline, then pauses, and then moves to the left. So if I can find the difference between s of 1 and s of 0, and then the absolute value of the difference between s of 3 and s of 1, I've got the total distance traveled, because I'm not worried about displacement in this example. So let's look back up at the original position function. Original position function, if I plug in a 0, the original position is -2.5. Okay? The position after 1 second would be 1 minus 7 plus 11 minus 2.5. So that would be 12 5, that'd be 2.5. Okay, so our position change from 0 to 1 was right 5 units. Okay, now let's find the position after 3 seconds. That would be 27 minus 63 plus 33 minus 2.5. Okay, so that's going to be, oh gosh, 50, 60. That'll be 60 minus 63 minus 2.5. So it's going to be negative 5.5. Okay, so from S of 1 to S of 3, okay, it looks like we went left 10.5 units. Oops, I'm sorry. From 2.5 back to negative 5.5 would be left 8 units. So if I went right 5 units and then left 8 units, we would have traveled a total of 13 units. Or in this case, I don't think it gives us units. That's fine. So we could just say that the particle traveled, what did we say? 13 units, was it? I think that's what it was. I can't even remember now. Yep, 13 units. Okay, so we started at 2.5. After 1 second, particle was at started at negative 2.5, traveled to positive 2.5, and then back to negative 5.5. Okay, here you go, guys. That is distance traveled and some particle motion. Didn't go over displacement, but in this case, I guess we could talk about displacement. The total displacement here would be started at negative 2.5, ended at negative 5.5, and those two are 3 units apart. So displacement would be 3 units. All right, that's it. Have a great day. We'll see you in the next video.